Rate of change and linear equations. So we're going to talk about how our variables change with each other, and we're calling that our rate of change. So how fast is something changing? So the rate of change, if x is the independent variable and y is the dependent variable, then the rate of change is the change in y over the change in x. So how is our y variable changing compared to how our x variable is changing? We're comparing the two with each other, and we're using that as a rate. Typically, we'll talk about this rate of change in real-world problems as the two that we have here. So let's take a look at how to find the rate of change. Use the table to find the rate of change. Explain the meaning of the rate of change. So in this particular table, we have time driving as x and the distance traveled as y. So our input, our output, our independent variable, our dependent variable. So we have 2, 4, and 6 as our input, 76, 152, and 228 as our output. Our independent and our dependent. So if we take a look at how is each of these changing, and somewhere my +2 has vanished here. So for each of these, our independent variable is going up by 2. Our dependent variable is going up by 76 each time. So this is pretty consistent as we go along here. So again, the change in y over the change in x, so 76 over 2, output over input. We can simplify that, as we always do with fractions, into 38 over 1. So what does this mean? That the car is traveling at a rate of 38 miles per hour. And notice those are my labels that I have here. My output, my dependent is my miles, and my independent is my hours. So miles per hour is my rate. Let's take a look at finding the rate of change from a graph. So here we have a graph comparing our year to the number of passports that have been handed out in millions. Notice the label on here, this is in millions. We're going to ask to find the rate of change for 2002 to 2004 and 2004 to 2006. Now you notice here that on this graph we've got two lines here, and the lines they're definitely in different chunks here. So I have a segment from 2002 to 2004 and then another segment from 2004 to 2006. This is not purely linear. They are in different segments. So we're going to find the rate of change in each of those segments. So for 2002 to 2004, again, we're going to do the change in y over the change in x. So I'm going to do my 8.9 minus 7. So that's the difference. That's the rate of change. That's the amount that it has changed in my output over my input, 2004 minus 2002. So come up with 1.9 over 2. Simplify that to 95 hundredths. What does that mean? It means there's been an increase of 95,000 passports per year. So again, it's passports per year, our dependent over our independent. For 2004 to 2006, again, I'm going to take my output, my dependent variable, and find the change, 12.1 to 8.9. I'm also going to do the same thing with my independent, my input, 2006 minus 2004. When I do the math here, I have 3.2 over 2, which simplifies to 1.6. What does that mean? There's an increase of 1,600,000 passports per year. So talking about our rate of change as far as a table real-world situation and as far as a graph real-world situation, we can find rate of change in either of those situations. Now let's take a look at deciding if these functions are linear. So we're still talking about rate of change, but when we talk about if it's linear, we're asking is the rate of change consistent all the way through? So we had that real-world graph of passports, and we had two line segments. They didn't make a straight line. They had kind of a hitch in the middle of them. We want to know, is this a consistent line all the way through all of these points? So again, we're going to look at the change in y over the change in x. So here we look at our change in y, 12 minus 6, and our change in x, 2 minus 1. And we notice that we end up with a rate of change of 6. If I take my next 2 points, 18 minus 12 gives me 6. 3 minus 2 gives me 1. That's a rate of change of 6. 24 minus 18, my dependent variables on top, gives me 6. 4 minus 3 gives me 1. That also gives me 6. So I have a consistent rate of change here of 6. I should also be able to take any two random points off of this table and come up with the same rate of change. So for instance, if I use the first point and the last point, and I can go either direction here. So if I do 6 minus 24, that gives me negative 18, and 1 minus 4 that gives me -3. -18 over -3, when I simplify that, gives me 6. So I always end up with a rate of change of 6 here, no matter which points I start at and which point I end up at. Which means this has a consistent rate of change, which means that line is going to be one straight line on this whole entire graph. So the rate of change is constant, which means that the function is linear. So if we have a constant rate of change throughout all of the points that we're looking at, we have a linear function. It's a function already. It's linear when the rate of change is consistent all the way. Let's take a look at another table. So again, I'm going to do the same thing here. I'm going to take my dependent, my output, and find the rate of change, so 1 minus 5, and my independent, 2 minus a -10, and I simplify that to a fraction of a rate of change of -1/2. So rate of change of -1/2. Now I'm going to take 2 more points. I'm going to do my -4 and 1. So -4 minus 1, 6 minus a -2. I get -5 over 8. So notice here I'm not coming up with the same rate of change twice. I have different rates of change, so I could stop right there. The minute I find that I have some of these rates of change are different, we realize that it's not a constant rate of change, which means the function is not going to be linear. So these are functions. The input has something to do with the output, and we never have more than the input going to more than one output, but they're just not linear on a graph.